Okay, so to continue on congruences, because last time we looked at congruences, modular congruences, and so we're going to continue on this in this video and, in many consequent videos. So last time it was specifically introduction to congruences and some divisibility tests, and, we're not going to dwell longer on divisibility tests in this video, but instead we're going to look at a few interesting theorems of modular congruences, and you do well to remember them because some of them we might be using less than others, but they're generally pretty important theorems in number theory. So as a reminder, if you haven't watched last video maybe, even though you should before this one, is we say that A is congruent to B mod M, if and only if M divides A minus B. So M divides the difference of A and B. And if that definition is unfamiliar to you, you should go look at last video. And remember as well that congruences can also be thought of as A and B leaving the same remainder when they're divided by M. Since we'll keep using congruences again and again, you really should make sure you understand the basics from last video before you keep going. So with that, let's actually prove some theorems. So Fermat's little theorem is the first one we're going to be proving. And, you shouldn't get hyped up. This is not the more famous Fermat's last theorem. So Fermat's last theorem, before I get to Fermat's little theorem, if you've heard of it, it's that there is no solution. Well, you've got, Pythagoras tells you that x squared plus y squared equals z squared. That has solutions because we know that right angle triangles follow this this law. But Fermat's last theorem says that there's no integer solutions to x to the n plus y to the n equals z to the n for any n that's bigger than 2. Now that's not what we're going to be looking at, especially because the proof of that is way, way beyond any of us. And so we're going to be looking at Fermat's little theorem, which is a lot simpler, and it has nothing to do with Fermat's last theorem. So Fermat's little theorem is that a to the p is congruent to a mod p for a prime p. And equivalently, a to the p minus 1 is congruent to 1 mod p. Now I say equivalently because p is a prime, right? Which means that since a is co-prime to p, because p is prime, and a is not p itself, p is going to be co-prime to p. So that means that we can take the inverse of a modulo p and multiply by that on both sides. So bring a to 1 and bring a to the p to a to the p minus 1. And once again, we can do that because a has an inverse modulo p. So keep in mind, I'm saying that a is not equal to p or is not a multiple of p because in the case where a is a multiple of p, then a to the p is obviously congruent to a mod p because a itself is just going to be 0 mod p. So we've got 0 to the p is congruent to 0, and that's obviously true when p is not 0, but p is not 0 because it's prime. So anyways, let's look at the proof itself. So first we're actually going to have to prove a useful lemma, and it's a lemma that you might use sort of in other contexts with congruences as well, so it's also just a useful theorem on its own. And it's called the freshman's dream. And it's got to do with looking at the congruence of x plus y to the p, and noting that it's going to be congruent to x to the p plus y to the p. Now note that that's, not true for equality, and we all hope that it was true in high school, but it's, you have to take the binomial theorem to actually open this up. And so we're going to use the binomial theorem to actually prove this lemma here. So if we look at the proof of a lemma, by the binomial theorem, we take x plus y to the p, and that's going to be the sum from k equals 0 to p, of p choose k times x to the I times y to the p minus I. So if you don't remember this formula or you're unfamiliar with it, maybe look back at video 5. Video 5. And so if I expand this out, I can remove the index where k equals 0 and the index where k equals p, and that's going to give me x to the p and y to the p. And then I'm left with a sum indexing from k equals 1 to the p to the minus 1, okay? Now, we saw in video 6 that p divides p to the k. Well, p choose k, sorry, for 1 is smaller or equal to k and smaller or equal to p minus 1. So that means that for all of those, because in this case k is smaller or equal to 1 and smaller or equal to p minus 1, we've got that we've got a sum including p choose k. So that means that p is going to divide this whole sum here. P is going to divide that. I'm just going to write it like this. And remember that when p divides something, that thing is congruent to 0 mod p. So that means we've got x plus y to the p is congruent to x to the p plus y to the p plus this term here, mod p. And we've got that this term is congruent to 0 mod p, so in the end it's just going to be congruence to x to the p plus y to the p mod p. So that's a useful little theorem to have, and in general just to work with powers and congruences. So try and remember this one as well. So continuing with the actual proof of the main theorem, we're going to do it by induction. So the base case for a equals 0 is actually pretty obvious, and you can do that by yourself. Just note 0 to the p is congruent to 0 mod p. That's just obviously true. So we're going to assume that it holds for any a, and we'll show that if it holds for a, then it must hold for a plus 1, and that'll allow us to do induction. So a plus 1 to the p minus a plus 1 is congruent to a to the p plus 1 minus a minus 1. So how did I do this? Here, I used the freshman's dream for this expansion, right? So that's the lemma we just proved. This guy is congruent to this guy. And here I've just expanded the parentheses. So then, using that, we've just got a to the p plus 1 minus a minus 1. I can cancel out those 1s here. And so I'm left with a to the p minus a. And a to the p minus a by the induction hypothesis is congruent to 0, because the induction hypothesis tells us that a to the p is congruent to a. And so that means that a to the p minus a is going to be congruent to 0. So we've shown that a plus 1 to the p minus a plus 1 is congruent to 0, which is the same as showing that a plus 1 to the p is congruent to a plus 1 mod p. So what we've got here. And so that completes the induction. Well, it completes it at least for all a that are natural numbers. If we want to show it for all integer a's, well, we don't actually really have to because we're dealing with congruences here. We could have performed the similar arguments, but with a minus 1 instead. And it's really just the same process. We get different canceling because here's going to be a minus 1 turning into a plus, and here this minus 1 stays a minus. So it would have worked because p is odd. So that's how you prove Fermat's little theorem. So before we go into the next theorem, I want to talk about residue systems. And so last video I briefly mentioned that a complete residue system mod m is just a collection of distinct integers mod m, such that all integers are congruent to some element of that system. So when I say distinct integers mod m, that just means that if I take any two integers a and b, right, then they're just not congruent to each other mod m in that system. And I'm talking about distinct ones, right? So if I take, of course, a is going to be congruent to a, but for any other distinct one in the complete residue system, it has to be distinct mod m. And so any integer is going to be congruent to some element of that system. So now we're going to define a reduced residue system mod m. And so a reduced residue system mod m is a set of integers, so that's the same till now, and it's going to be a1, a2, all the way to ak, such that for all I, the greatest common divisor of ai and m is 1. So that means that each of these are coprime to m, and that any integer n that is coprime to m must be congruent to some ai mod m. Okay? So it's a collection of coprime integers to m, well, coprime naturals to m, well, integers are, yeah, and we're going to have to take the condition that any integer n coprime to m must be congruent to one of these. So it's the same as here, except we're adding this sort of coprimality condition in both cases. So if we take a complete residue system, and I pick the subset of coprime integers to m, then I'm actually going to get a reduced residue system. I'll leave that as a proof, as an exercise. We're not going to prove it here. So let's take an example. If I take m equals 14, right, we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is going to be a complete residue system. And the way I mentioned complete residue systems last video was when I mentioned the integers modulo m. And you'll notice if I add, square brackets around each of these, I'm actually going to have the integers mod 14. So, we already know that this is a complete residue system. And so if I take the subset of coprime integers, I'm going to get 1, 3, 5, 9, 11, and 13, and you can check whether those are coprime to 14. And that's going to be a reduced residue system. So what's Euler's totient function, which is going to be useful for our next theorem? So Euler's totient function is just counting the number of elements in a reduced residue system mod m, and it's called Euler's totient function evaluated at m. And so it's denoted by phi of m. This here is phi, the Greek letter phi. So since the integers between 0 and m that are coprime to m form a reduced residue system, that are coprime to m. So we know that the ones between 0 and m that are not coprime to m, or that are just any of those integers, that's going to form a complete residue system because those are the integers mod m. And then if I take the subset of those that are coprime to m, then I get a reduced residue system. And so phi m counts exactly those integers. So phi m, what might be easier for you to think about is that it counts the number of naturals that are coprime to m and that are smaller than m. So let's look at a few examples to just make that concrete. So if I take phi of 1, right, and I just have to check 1, and 1 is co-prime to 1 because the greatest common divisor of 1 and 1 is 1, so that's easy. Then phi of 9, I claim is 6. Well, we've got that 1 is going to be part of the residue system. We're also going to have, if we look at 2, 2 works, it's also co-prime to 9. If we look at 3, it doesn't work, so I'm not going to put it in here. If I look at 4, it's going to work. If I look at 5, it's going to work. If I look at 6, it's not going to work because it has a greatest common divisor of 3. If I look at 7, it's going to work. And if I look at 8, it's going to work. So I've got 1, 2, 3, 4, 5, 6 of those, and so that gives me that phi of 9 equals 6. And in general, phi of p, where p is a prime, is going to be p minus 1. So that makes sense, right? I mean, because every integer is co-prime to a prime, unless it's a power of that prime. So all the integers that are smaller than a prime are going to be co-prime to the prime itself. So, and there's p minus 1 of those. So that's why we've got 5p equals p minus 1. And we're going to look later at how to actually evaluate phi of m, more generally, for any kind of integer that's prime factorable. And so we'll likely look at that in the next video, but it might be in 2 videos. So with that in mind, with those tools, we can actually look at Euler's theorem. And so Euler's theorem is just a more powerful sort of Fermat's little theorem. And it says that if the greatest common divisor of a and m equals 1, so we're not even considering a p here, then we've just got that a to the totient function of m is congruent to 1 mod m. So Fermat's little theorem is a special case of this, right? So when I replace m by p, then I've got that the greatest common divisor is equal to 1, so I can just forget that condition. And we just saw that the totient function of p is p minus 1. So this theorem here would give me that a to the p minus 1 is congruent to 1 mod p, which is exactly what Fermat's little theorem says. So it's just a special case of Euler's theorem, and we could have maybe proved Euler's theorem first, and then the proof of Fermat's little theorem would have been a lot easier. But it's nice to also see the other proof of Fermat, so that's why I did it first. So let's look at a proof for this. So first we're going to show a lemma, and the lemma is that if the greatest common divisor of a and m is equal to 1, and we have R is R1, R2, all the way to Rk, and that's going to be a reduced residue system mod m. And note that k here is going to be phi of m, because there's phi exactly counts the amount of elements of this reduced residue system. Then a is equal to a times R1, a times R2, so I'm just multiplying all of these by some constant a, is also going to be a reduced residue system mod m. So that's going to help us say something about the totient function. So let's see what we can do with that, if PowerPoint would load. Okay, so the proof of a lemma. So the size of a is already as we need, right? Because we've already got 1, 2, 3 all the way to k. So we don't even need to show that that it has the size of a reduced residue system. So all we actually really need to show is that its elements are distinct mod m and that they're co-prime to m. So first, to show that they're distinct, to show that they're co-prime, sorry, we know that if the greatest common divisor of Ri and m equals 1, when this is true, right, because R was a reduced residue system, and the greatest common divisor of a and m equals 1, and that's true by assumption, then we've got that the greatest common divisor of a times Ri and m is equal to 1, because this is the a that we're considering for Euler's theorem. And so this is just, a theorem that we've proved before alongside of video 2, I think, and it's just that we can take this these products here and get that the greatest common divisor is also equal to 1. And so that's going to show us that all the elements of A are actually co-prime to M. So we've already showed that they're co-prime to M, that's done. Now we just need to show that they're distinct mod M. So if we have ARI is congruent to ARJ, we'll assume that, right? If I is not equal to j, and so we obviously want to get to contradiction, because that's what we're trying to show is not possible. Then we've got that M divides ARI minus ARJ by definition, and I can just factor A out of that to get A times Ri minus Rj. Now the greatest common divisor of A and M is 1, and so we've also seen a theorem with divisibility before. We have that M must divide Ri minus Rj because it doesn't divide A, and it doesn't have a greatest common divisor of A. So if it's co-prime to A, I can just get rid of the A and the divisibility here. And that's something we've seen as well. So you might want to go back to, I think, video 2 to see that. So we've got that M divides Ri minus Rj, and that implies that Ri is congruent to Rj. So actually this is equivalent to saying that Ri is congruent to Rj mod M. But that's a contradiction, right? Because if this happened, then the first residue system would not be a reduced residue system, and so it wouldn't work at all, and we'd have a contradiction. And so that's the end of the lemma proof. And so now we can actually get to proving the actual theorem. So let's do that. We choose a reduced residue system R, because we want to use the lemma we just proved, right? So R is going to be equal to R1, R2, Rk, same again, with k is equal to the totient function of m. And so by the lemma, and since the greatest common divisor of a and m is 1, we have that a is equal to a times R1, a times R2, all the way up to a times Rk, is going to be another reduced residue system, right? And that's the lemma we just proved. So because we've got two reduced residue systems, right, then these two are going to have to be permutations of each other mod m, right? Because any integer needs to be congruent to one of these if it's coprime to m. And all of those are coprime to m, which means they're all congruent to one of these. And it's the same the other way around. So actually, I've got, when I say they're permutations or rearrangements, it means formally that I can construct a bijection between R and A. And so they're rearrangements of each other in mod m. So hence, if I just multiply all of them, because multiplication is commutative, then I can just, realize that I can pair up each one of these with some one of them. And so in the end, I could just make a whole multiplication over all the elements, and that's just going to be the same thing. So that R1 times R2 times ... times Rk is congruent to AR1 times AR2 times ... times ARK, mod n. So I can factor out the a's here to get R1 times R2 times ... times Rk is congruent to a to the k, because I've got k of those a's, times R1 times R2 all the way to Rk. Now the greatest common divisor of Ri and m is 1. And so that means that I can reapply what I was talking about before with Ri and a, and in this case I'm just going to do it across the r's, and do multiple multiplication to get that the greatest common divisor of R1 times R2 times ... times Rk with m is going to be equal to 1. And so what that means is that we can cancel R1 times R2 times ... times Rk. And you would have proved that last video as homework. And in case you didn't do that, we can just realize that because the greatest common divisor is equal to 1, then I can this whole term here has an inverse modulo m. So I can just multiply by the inverse modulo m on both sides of its congruence, and so that ends up turning this into a 1 and turns this into a 1. And so we're only left with 1 is congruent to ak mod m. And so that's exactly what I have here. 1 is congruent to ak mod m. And k is just the totient function. That's what we have up here. So that implies that a to the totient function of m is congruent to 1 mod m. And so that's what we needed to prove. It's actually a pretty powerful statement, and we're gonna be using Euler's theorem later on when we talk about RSA encryption. And it's a very powerful and useful theorem. So now we're going to talk about Wilson's theorem. And so, I went back a slide. Okay. So Wilson's theorem, once again, has to do with primes. And we're going to say that if p is a prime, then p minus 1 factorial is congruent to 1 mod p. And if you don't remember factorial, which, you should, but the factorial is just 1 times 2 times 3 times ... times p minus 1. Okay? So I just take all the natural numbers from 1 to p minus 1, and I multiply them, and that's a factorial. Okay, so let's prove that. Once again, we're going to have to do a lemma, and first we can look at a simple case, which is p equals 2. And p equals 2 is easily seen to be true, because we've got 2 minus 1 is 1, 1 factorial is 1, so 1 is congruent to 1 mod p, and that's, well, mod 2. And so that's pretty obvious. And so once we take care of a p equals 2 case, we can just focus on odd primes, okay? So let us prove a lemma for that. And we're going to say that the congruence x squared congruent to 1 mod p only has the solution x is congruent to 1 or x is congruent to minus 1. So it says x is congruent to plus minus 1 in one statement here, just to make it shorter. But that's really two statements. It's either x is congruent to 1 or x is congruent to minus 1 mod p. So let's look at proof of that. Well, p divides x squared minus 1, right? That's what we've got here. And so then I can factor x squared minus 1 with a difference of 2 squares, and that's a pretty common factorization. If you're not familiar with that, you should look up difference of 2 squares. You can also just FOIL this out and to realize that it's the same thing. So we've got p divides x plus 1 times x minus 1, okay? And so what that means is that, p itself is irreducible into factors, which means it can't, you can't have factors of p and x plus 1 and factors of p and x minus 1 that would make p divide this whole thing, because p is irreducible. So p either divides x plus 1 or it divides x minus 1. Or I guess it could divide both, but that can only happen actually if p is equal to 2. And we're only considering the case where p is not equal to 2. So you've got either p divides x plus 1 or p divides x minus 1. And so that implies that x is congruent to plus minus 1 mod p. which is what we're trying to show. So with that in mind, let's see what we can do to prove the whole theorem. If, once again, PowerPoint would load. Yeah, here we go. So, we're going to note that x squared is congruent to 1 mod p would imply that the greatest common divisor of x and p is 1. And that's again something you would have shown in last video. It was an exercise that I gave, and it was to say that a be congruent to 1 mod m. Here's mod p, but this is true, for any m. Would imply that a and b are both congruent to 1 mod p. So here we've got that x is congruent to 1 mod p, right? That x, the GCD of x and p is equal to 1. So what it further implies is that x actually has the inverse, x minus 1 is congruent to x mod p. Because keep in mind, I could deconstruct this into x times x is congruent to 1. And the definition of an inverse is that, if I have the inverse of a, it's a times a minus 1 is congruent to 1. If we can find one of these, then it's the inverse of a. And in this case, well, we found one, but it's x itself. So x is its own inverse, actually. So you've got that x minus 1 is congruent to x mod p. So when we have x squared is congruent to 1, we get this, and we get that. These are the two results we get from this that are important. So hence, in mod p, 1 and minus 1 do not have distinct inverses, and they're the only such integers mod p. So why do I say that? Well, because with the lemma that we just proved, we showed that if x squared is congruent to 1, that's only true if x is congruent to plus minus 1. I'm not going to write the mod p, but you get it. And so that means that for x equals 1, I have that the inverse of 1 is 1. And for x equals minus 1, I have that the inverse of minus 1 is minus 1. And I don't have any other I don't have any other integers mod p that have this property that they are their own inverses, because otherwise it'd be a solution to x squared is congruent to 1 mod p, right? And that wouldn't work because we've shown that the only solutions are 1 and minus 1. So 1 and minus 1 have non-distinct inverses, and they're the only such integers mod p. So now let's take big P is equal to 1 all the way up to p minus 1, and that's going to be a reduced residue system mod p, because keep in mind 1 all the way to p minus 1, these are all co-prime to p. And so we can only pair up any elements of a and p, we can pair up any elements of a and p with a distinct inverse a to the minus 1 mod p, which is also going to be in big P. So keep in mind, I say distinct, but this is not going to be true for 1 and minus 1, right? And minus 1 isn't in this system, but it's congruent to p minus 1. So 1 and p minus 1, they're not going to have distinct inverses, but all the other ones in here, they need to have an inverse mod p, because they're co-prime with p, so we're going to have an inverse mod p, but it can't be the same inverse, because otherwise it'd have to be 1 or p minus 1. So that means that they're going to have a distinct inverse, a to the minus 1 mod p, and so I can pair them up with their inverse. And once again, the only ones we cannot do this for are 1 and minus 1, and so in this case it's going to be p minus 1. And so hence, p minus 1 factorial, this is here, it's just the product of all these elements here, which are in the reduced residue system. But I can rearrange them to note that if I take a1 and say a1 is 2, for example, then I have some distinct inverse, which is going to be a1 to the minus 1. And I can do the same for the next one, a2, and the same for a3, and all the way up to ak, with k is just going to be p minus 1 over 2. And so, in this case, I've got all this times minus 1 times 1, because these guys can't be paired up. But all those got to go to 1. So this goes to 1, this goes to 1, and so on. And so in the end, I'm only left with minus 1 times 1, which is congruent to minus 1 mod p. And so that's exactly what we wanted to prove, that p minus 1 factorial is congruent to p minus 1, is congruent to minus 1 mod p, which is the same as p minus 1, I guess, but yeah. So now, Wilson's theorem actually has a pretty nice application which we can do in this video, and it helps us to solve the congruence x squared is congruent to minus 1 mod p. We're going to do that with Wilson's theorem then. So the congruence x squared is congruent to minus 1 mod p is solvable if and only if p is equal to 2, or p is congruent to 1 mod 4. So p being congruent to 1 mod 4 means we can write p as 4k plus 1, right? I'm just writing it like this, okay. So let's look at the proof of this. So the p equals 2k is pretty easy, right? And I mean, you can just look at it. If I have got mod p, well, 1 squared is congruent, it's congruent to minus 1 mod 2, because minus 1 is congruent to 1 mod 2. I mean, mod 2 is generally not very interesting, because I only have to consider really two distinct integers, the odds and the even. So the p equals 2k is pretty easy. So now we just have to show that there's no, well, not just have to show, but we're first going to show that P is congruent to 3 mod 4 is not possible. And then after that, we'll show that P is congruent to 1 mod 4 has at least one solution, and then we'll be done. Now, the reason why we'll be done is because the P equals 2 case takes care of P is congruent to 0 and P is congruent to 2 mod 4. Because if P is congruent to 0 or P is congruent to 2 mod 4, then P is even. But since P is a prime, the only even prime is P equals 2. So it takes care of those cases. And we're only left with P is congruent to 1 or P is congruent to 3 mod 4. So let's assume that x squared is congruent to minus 1 mod P for some x coprime to P equals 4k plus 3, right? And I've written P as 4k plus 3 because P has to be congruent to 3 mod 4. Now we can rewrite P minus 1 a little bit, and we're going to rewrite it. P minus 1 is going to be 4k plus 2, and I can factor out a 2 here to get 2 times 2k plus 1, okay? So now you'll note that x squared to the 2k plus 1, well, x squared is congruent to minus 1 mod P, so that's going to be congruent to minus 1 to the 2k plus 1. And because 2k plus 1 is an odd number, because remember that I've reduced an even number to something, then I've got minus 1 is congruent to minus 1 mod P. Yet, we also have that x squared to the 2k plus 1, well, that's going to be x to the 2 times 2k plus 1, and 2 times 2k plus 1 is P minus 1. So that means that x to the P minus 1 is congruent to 1 mod P, right? So we've shown two things. We've shown that x squared to the 2k plus 1 is congruent to 1 mod P, but it's also congruent to minus 1 mod P. Now that would be a contradiction unless P was equal to 2, and we're specifically considering P is not equal to 2. So that's a contradiction. And so it's impossible if P is congruent to 3 mod 4. We can't have a solution because it just doesn't work. So now let's look at the case P is congruent to 1 mod 4. Well, this is where we use Wilson's theorem. We've got P minus 1 factorial is going to be congruent to minus 1 mod P. That's just writing out Wilson's theorem, okay? So I can expand the factorial into 1 times 2 all the way times P minus 1 is congruent to minus 1 mod P. And I can further rewrite that as 1 times 2 times dot 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 times P minus 1 over 2. And I can do that because P is odd, so that's going to be even. And similarly for P plus 1 over 2. And then I can keep going all the way to P minus 1, okay? And so I've just split it in half around halfway through this product. So now we're going to do something interesting. If PowerPoints would load. Okay, yes. So I'm just rewriting the result here. So we're going to let x is equal to 1 times 2 all the way times P minus 1 over 2. So that this here is going to be x, right? And we're just naming a variable at this point. And so now we're going to note, now this is maybe a little cumbersome, but we're going to note that P minus 1 is congruent to minus 1, right? And that's congruent to minus 1 times 1 mod P. That's pretty obvious, okay? P minus 2 is congruent to minus 2, and that's congruent to minus 1 times 2 mod P. And in general, you know, we can keep going all to P plus 1 over 2, because P plus 1 over 2 is just P minus 1 over 2. And so that's going to be congruent to minus P minus 1 over 2, which is congruent to minus 1 times P minus 1 over 2. Okay? So that means that P plus 1 over 2 times P plus 1 over 2 plus 1 times P plus 1 over 2 plus 2, and so on all the way to P minus 1. So that's just this second half here. That is going to be congruent to minus 1 to the P minus 1 over 2 times x. So why did I do that, right? So for each of those, it's congruent to minus 1 times 1, so that's for this one. Then I've got minus 1 times 2, and all the way up to minus 1 times P minus 1 over 2. So the 1 times 2 times 3 is going to come after, then times 4 all the way to P minus 1 over 2. That's the same as x, so that's what we wrote here. And these minus 1s here, I'm going to have exactly P minus 1 over 2 of them. So that's why I've got minus 1 to the P minus 1 over 2 times x, okay? And P minus 1 over 2 is an even number, okay? So that means that that's going to leave us with that the whole thing is congruent to x mod P. So that's all we needed. And so therefore, P minus 1 factorial is, oh, by the way, the reason why P minus 1 over 2 as an even number, maybe I should specify, is because here we're assuming that P is congruent to 1 mod 4, right? And if P is congruent to 1 mod 4, then you can write it as 4k plus 1, which means that P minus 1 can be written as 4k. So P minus 1 over 2 is going to be 2k, which is the form of an even number. Okay, that was just precision here. Okay, so therefore P minus 1 factorial is going to be congruent to x squared, which is going to be congruent to minus 1 mod P. Why do I say that? Well, that's because P plus 1 over 2 all the way to P minus 1, that's x. This is x, because that's what we've just shown here. And this is also x, which is by definition of x. And so this whole thing is p minus 1 factorial, so that's congruent to x squared. And p minus 1 factorial is congruent to minus 1 mod p. So that means that x equals p minus 1 over 2 factorial, so that's just splitting the thing halfway through, solves the congruence x squared is congruent to minus 1 mod p if p is congruent to 1 mod 4. So that shows that there's a solution for p congruent to 1 mod 4, and so that completes the whole proof. And finally, to complete this off on this video, we're going to just show that how many primes there are of the form 4k plus 1. And what we claim is that there are infinitely many primes of this form. And we're going to show a much, well, if we get to that point, we're going to show a much stronger theorem, actually, which shows that there are infinitely many primes of the form p is congruent to 1 mod any n. But that takes a lot more work and uses cyclotomic polynomials, and we'll do that maybe in some later video, and it'll take some time before we get there. But so here's a special case where n equals 4. Let's look at the proof then. So, kind of like when we did the Euclid proof for infinitely many primes, or the Euler proof for that matter, we're going to assume that we have finitely many primes of this form, and then we're just going to get to a contradiction, okay? So we're going to consider a positive integer, n, which is going to be equal to 2 times p1 times p2 all the way to pn. So we're multiplying all these primes, which we say are the only primes of this form, multiply them by 2, and we're going to square that. And then we add 1 to the whole thing. Now n is odd, and we know that because here we've got 2 times something, and then the whole thing is going to be plus 1, so that's a form of an odd number. And it's bigger than 1, I mean that's pretty obvious. So that means that it has an odd prime factor. And that odd prime factor is going to be q. And we're going to say that it's not equal to any of the pi. And why is that? Well, that's because each of the pi's divide n minus 1, right? Because if I take n minus 1, then I'm only left with this guy here. So each of the pi's divide n minus 1, but q we want to divide n, and q can't both divide n and n minus 1 at the same time. So, except if it was 1, of course, but I mean, that's not a prime. Okay, so we've got q divides n, which implies that 2 times p1 times all the way to pn squared is congruent to minus 1 mod q. And that's because, 2 p1 all the way to pn squared is plus 1 is congruent to 0 mod q, okay? So we've got a square number here. This is a square number, and so we've got x squared is congruent to minus 1 mod q, where x is 2 times p1 all the way to pn squared. And so that means that this equation, where x, we're just looking to solve x, has a solution that's bigger than 2, because that's n. Well, that's n minus 1. And so since we have that solution, by the above results, q is going to be congruent to 1 mod 4. And that's a contradiction, right? Because if q is congruent to 1 mod 4, we know that q is a prime, and q can be written as 4k plus 1 then. But then we've got a prime of form 4k plus 1 that's not accounted by the finitely many primes that we've written here. So we've generated a new prime, which doesn't fit our sort of full series that we had. So that finishes the proof of that. And so that's it for this video.